Today we're given a list of instructions that potentially modify an X register. The X register starts out with the value 1, and then the no-op instruction takes one cycle. That's why there's one number in this line, but doesn't modify the number. That's why it stays 1. And the add X instruction takes 2 cycles, and then finally adds 3 to the X value, giving us 4. And the next add instruction also takes 2 cycles, and then 4 minus 5 is minus 1, of course. Okay, so I start out with a transient empty vector. It's simply more efficient to conj onto a transient vector. And the X register starts at the value 1 as per the spec. And then here we pass the instructions, a long list of vectors with a string for the instruction and an int for the argument, or nil in the case of no op. And then we destructure them as usual. If there are no more instructions, then we conj the current value of x onto the result and then turn it back into a persistent version. And that's this conj is only interesting for the -1. That simply makes the example more understandable. It's not actually required for the part 1 and 2 answers. Okay, and if there are still instructions, or at least one, we check which one it is. If it's a no-op, we recur by conjing x onto the result. That gave us this 1, if you will, and the rest stays the same. And if it's an add instruction, then we conj x twice onto the result. So we reduce conj result and then 2 repetitions of x. That, if you know a simpler way of doing it, let me know. Okay, and the argument, of course, is added onto x. That's why the value changes from 1 to 4 and from 4 to -1. Right, then we have our X register values, and then for part 1, we must compute the signal strength. That's just a multiplication of 2 numbers, the cycle number and the value of the X register. So here we have all the values of our X register, and here the range 1 from 1 to long max value is a very long range. And then we simply map the multiplication over that, right? We already learned that we can pass 2 collections to the map function. Okay, and then we start at the 20th cycle. That's why I drop the first 19. And then we're only interested in every 40th cycle. So in this case, that would be the first 19 would be dropped until here. And then we pick the 420, drop the next 39, then pick the number, then drop 39 again, and so on. That's basically how it works. Yeah, that works quite well. Okay, then the next function, screen pixel, is giving a cathode-ray tube position on the x-axis and the middle of a sprite in the x-axis. The sprite has a width of 3, and we can simply subtract them from one each other and then check is the difference -1, 0, or +1. That's when they intersect, and then we have to draw a hashtag. Otherwise, we have to draw a dot. And it's quite nice that the case allows us to pass multiple test constants for one particular result. That's similar to case fall through, or how you would solve that with case fall through in other languages like C. Right, and then for part 2, that's a bit more complicated. So we start with our X register values again, and then I cycle the range 0 to 40. So 0 to 40 is 0 to 39, then it ends. And if we cycle that range, then after 39, we go back to 0 again. That's basically the line break in our Cathode-Ray, right? Go to the next line, X starts at 0 again. And then we map the screen pixel function over that. So is the middle of the sprite near enough to our X value of the Cathode-Ray tube? Right. And if we execute that, then we get a very long sequence of hashtags and dots. That's not quite so easy to decipher. So what do we do next? We partition it into groups of 40. Then we have the first line as a sequence, the second line as a sequence, the third line as a sequence of characters, and so on. And to make it even more readable, we map the string join function over all those lines to get one string per line and not a bunch of characters. And then it looks like this, exactly as we wanted. And if you do that for your own personal input, then you should see 8 capital letters.